function mathematics.
In mathematics, a function is a relation between a set of inputs and a set of permissible outputs with the property that each input is related to exactly one output. An example is the function that relates each real number x to its square x2. The output of a function f corresponding to an input x is denoted by f. In this example, if the input is 3, then the output is 9, and we may write f equals 9. The input variable is sometimes referred to as the argument of the function. Functions of various kinds are the central objects of investigation in most fields of modern mathematics. There are many ways to describe or represent a function. Some functions may be defined by a formula or algorithm that tells how to compute the output for a given input. Others are given by a picture, called the graph of the function. In science, functions are sometimes defined by a table that gives the outputs for selected inputs. A function could be described implicitly, for example as the inverse to another function or as a solution of a differential equation. The input and output of a function can be expressed as an ordered pair, ordered so that the first element is the input, or tuple of inputs, if the function takes more than one input, and the second is the output. In the example above, f x equals x2, we have the ordered pair 3, 9. If both input and output are real numbers, this ordered pair can be viewed as the Cartesian coordinates of a point on the graph of the function. But no picture can exactly define every point in an infinite set. In modern mathematics, a function is defined by its set of inputs, called the domain. A set containing the set of outputs, and possibly additional elements, as members, called its codomain. And the set of all input-output pairs, called its graph. Sometimes the codomain is called the function's range, but warning, the word range is sometimes used to mean, instead, specifically the set of outputs. An unambiguous word for the latter meaning is the function's image. To avoid ambiguity, the words codomain and image are the preferred language for their concepts. For example, we could define a function using the rule f x equals x2 by saying that the domain and codomain are the real numbers, and that the graph consists of all pairs of real numbers, x, x2. Collections of functions with the same domain and the same codomain are called function spaces, the properties of which are studied in such mathematical disciplines as real analysis, complex analysis, and functional analysis. In analogy with arithmetic, it is possible to define addition, subtraction, multiplication, and division of functions, in those cases where the output is a number. Another important operation defined on functions is function composition, where the output from one function becomes the input to another function.
Introduction and examples.
For an example of a function, let X be the set consisting of 4 shapes, a red triangle, a yellow rectangle, a green hexagon, and a red square. And let Y be the set consisting of 5 colors, red, blue, green, pink, and yellow. Linking each shape to its color is a function from X to Y. Each shape is linked to a color, that is, an element in Y, and each shape is linked, or mapped, to exactly one color. There is no shape that lacks a color and no shape that has 2 or more colors. This function will be referred to as the color of the shape function. The input to a function is called the argument and the output is called the value. The set of all permitted inputs to a given function is called the domain of the function, while the set of permissible outputs is called the codomain. Thus, the domain of the color of the shape function is the set of the 4 shapes, and the codomain consists of the 5 colors. The concept of a function does not require that every possible output is the value of some argument. For example, the color blue is not the color of any of the 4 shapes in X. A second example of a function is the following. The domain is chosen to be the set of natural numbers, 1, 2, 3, 4. And the codomain is the set of integers 3, 2, 1, 0, 1, 2, 3. The function associates to any natural number n the number 4. N. For example, to 1 it associates 3 and to 10 it associates 6. A third example of a function has the set of polygons as domain and a set of natural numbers as codomain. The function associates a polygon with its number of vertices. For example, a triangle is associated with the number 3, a square with a number 4, and so on. The term range is sometimes used either for the codomain or for the set of all the actual values a function has. To avoid ambiguity, this article avoids using the term.
Definition.
In order to avoid the use of the informally defined concepts of rules and associates, the above intuitive explanation of functions is completed with a formal definition. This definition relies on the notion of the Cartesian product. The Cartesian product of two sets X and Y is the set of all ordered pairs, written X, Y, where X is an element of X and Y is an element of Y. The X and the Y are called the components of the ordered pair. The Cartesian product of X and Y is denoted by XXY. A function f from X to Y is a subset of the Cartesian product XXY subject to the following condition: every element of X is the first component of one and only one ordered pair in the subset. In other words, for every X in X there is exactly one element Y such that the ordered pair, X, Y, is contained in the subset defining the function f. This formal definition is a precise rendition of the idea that to each X is associated an element Y of Y, namely the uniquely specified element Y with the property just mentioned. Considering the color of the shape function above, the set X is the domain consisting of the 4 shapes, while Y is the codomain consisting of 5 colors. There are 20 possible ordered pairs, 4 shapes times 5 colors, one of which is. The color of the shape function described above consists of the set of those ordered pairs, where the color is the actual color of the given shape. Thus, the pair, red triangle, red is in the function, but the pair, yellow rectangle, red is not.
Notation.
A function f with domain X and codomain Y is commonly denoted by. In this context, the elements of X are called arguments of f. For each argument X, the corresponding unique Y in the codomain is called the function value at X or the image of X under f. It is written as f, X. One says that f associates Y with X or maps X to Y. This is abbreviated by. A general function is often denoted by f. Special functions have names, for example, the signum function is denoted by sgn. Given a real number X, its image under the signum function is then written as sgn, X. Here, the argument is denoted by the symbol X, but different symbols may be used in other contexts. For example, in physics, the velocity of some body, depending on the time, is denoted v, t. The parentheses around the argument may be omitted when there is little chance of confusion, thus, sin X. This is known as prefix notation. In order to specify a concrete function, the notation, an arrow with a bar at its tail, is used. For example, the above function reads. The first part can be read as f is a function from the set of natural numbers, to the set of integers, or f is a valued function of an valued variable. The second part is read x maps to 4 x. In other words, this function has the natural numbers as domain, the integers as codomain. Strictly speaking, a function is properly defined only when the domain and codomain are specified. For example, the formula f, x, equals 4 x alone, without specifying the codomain and domain, is not a properly defined function. Moreover, the function with different domain is not considered the same function, even though the formulas defining f and g agree, and similarly with a different codomain. Despite that, many authors drop the specification of the domain and codomain, especially if these are clear from the context. So in this example many just write f, x, equals 4 x. Sometimes, the maximal possible domain is also understood implicitly. A formula such as may mean that the domain of f is the set of real numbers x where the square root is defined, in this case x 2 or x 3. To define a function, sometimes a dot notation is used in order to emphasize the functional nature of an expression without assigning a special symbol to the variable. For instance, stands for the function, stands for the integral function, and so on.
Specifying a function.
A function can be defined by any mathematical condition relating each argument, input value, to the corresponding output value. If the domain is finite, a function f may be defined by simply tabulating all the arguments x and their corresponding function values f, x. More commonly, a function is defined by a formula, or, more generally, an algorithm, a recipe that tells how to compute the value of f, x, given any x in the domain. There are many other ways of defining functions. Examples include piecewise definitions, induction or recursion, algebraic or analytic closure, limits, analytic continuation, infinite series, and as solutions to integral and differential equations. The lambda calculus provides a powerful and flexible syntax for defining and combining functions of several variables. In advanced mathematics, some functions exist because of an axiom, such as the axiom of choice.
Graph.
The graph of a function is its set of ordered pairs f. This is an abstraction of the idea of a graph as a picture showing the function plotted on a pair of coordinate axes. For example, 3, 9, the point above 3 on the horizontal axis and to the right of 9 on the vertical axis, lies on the graph of y equals x2.
Formulas and algorithms.
Different formulas or algorithms may describe the same function. For instance, f, x, equals, x plus 1, x. 1, is exactly the same function as f, x, equals x2. 1. Furthermore, a function need not be described by a formula, expression, or algorithm, nor need it deal with numbers at all. The domain and codomain of a function may be arbitrary sets. One example of a function that acts on non-numeric inputs takes English words as inputs and returns the first letter of the input word as output. The factorial function is defined on the non-negative integers and produces a positive integer. It is defined by the following inductive algorithm: 0 is defined to be 1, and n is defined to be for all positive integers n, given that the factorial of the predecessor was already defined. The factorial function is denoted with the exclamation mark, serving as the symbol of the function, after the variable, postfix notation.
Computability.
Functions that send integers to integers, or finite strings to finite strings, can sometimes be defined by an algorithm, which gives a precise description of a set of steps for computing the output of the function from its input. Functions definable by an algorithm are called computable functions. For example, the Euclidean algorithm gives a precise process to compute the greatest common divisor of two positive integers. Many of the functions studied in the context of number theory are computable. Fundamental results of computability theory show that there are functions that can be precisely defined but are not computable. Moreover, in the sense of cardinality, almost all functions from the integers to integers are not computable. The number of computable functions from integers to integers is countable, because the number of possible algorithms is. The number of all functions from integers to integers is higher, the same as the cardinality of the real numbers. Thus most functions from integers to integers are not computable. Specific examples of uncomputable functions are known, including the busy beaver function and functions related to the halting problem and other undecidable problems.
Basic properties.
There are a number of general basic properties and notions. In this section, f is a function with domain x and codomain y.
Image and primage.
If A is any subset of the domain x, then f, A, is the subset of the codomain y consisting of all images of elements of A. We say the f, A, is the image of A under f. The image of f is given by f, x. On the other hand, the inverse image, or primage, complete inverse image, of a subset B of the codomain Y under a function f is the subset of the domain X defined by. So, for example, the primage of 4, 9 under the squaring function is the set 3, 2, 2, 3. The term range usually refers to the image, but sometimes it refers to the codomain. By definition of a function, the image of an element X of the domain is always a single element Y of the codomain. Conversely, though, the primage of a singleton set, a set with exactly one element, may in general contain any number of elements. For example, if f, x, equals 7, the constant function taking value 7, then the primage of 5 is the empty set but the primage of 7 is the entire domain. It is customary to write f 1, b, instead of f 1, b, that is. This set is sometimes called the fiber of B under F. Use of f, a, to denote the image of a subset A. X is consistent so long as no subset of the domain is also an element of the domain. In some fields, for example, in set theory, where ordinals are also sets of ordinals, it is convenient or even necessary to distinguish the two concepts. The customary notation is f for the set f, x, x, a. Likewise, some authors use square brackets to avoid confusion between the inverse image and the inverse function. Thus they would write f 1 and f 1 for the primage of a set and a singleton.
Injective and surjective functions.
A function is called injective, or one-to-one, or an injection, if f, a, f, b, for any two different elements A and B of the domain. It is called surjective, or onto, if f, x, equals y. That is, it is surjective if for every element y in the codomain there is an x in the domain such that f, x, equals y. Finally f is called bijective if it is both injective and surjective. This nomenclature was introduced by the Bourbaki group. The above color of the shape function is not injective, since two distinct shapes, the red triangle and the red rectangle, are assigned the same value. Moreover, it is not surjective, since the image of the function contains only 3, but not all 5 colors in the codomain.
Function composition.
The function composition of two functions takes the output of one function as the input of a second one. More specifically, the composition of f with a function g, y, z is the function defined by. That is, the value of x is obtained by first applying f to x to obtain y equals f, x, and then applying g to y to obtain z equals g, y. In the notation, the function on the right, f, acts first and the function on the left, g acts second, reversing English reading order. The notation can be memorized by reading the notation as g of f, or g after f. The composition is only defined when the codomain of f is the domain of g. Assuming that, the composition in the opposite order need not be defined. Even if it is, that is, if the codomain of f is the codomain of g, it is not in general true that. That is, the order of the composition is important. For example, suppose f, x, equals x2 and g, x, equals x plus 1. Then g, f, x equals x2 plus 1, while f, g, x equals x plus 1, 2, which is x2 plus 2x plus 1, a different function.
Identity function.
The unique function over a set X that maps each element to itself is called the identity function for X, and typically denoted by idx. Each set has its own identity function, so the subscript cannot be omitted unless the set can be inferred from context. Under composition, an identity function is neutral if f is any function from x to y, then.
Restrictions and extensions.
Informally, a restriction of a function f is the result of trimming its domain. More precisely, if S is any subset of X, the restriction of f to S is the function fs from S to Y such that fs, S, equals f, S, for all S in S. If G is a restriction of f, then it is said that f is an extension of G. The overriding of f, x, y by G, w, y, also called overriding union, is an extension of G denoted as f, g, x, w, y. Its graph is the set theoretical union of the graphs of G and fx\w. Thus, it relates any element of the domain of G to its image under G, and any other element of the domain of f to its image under f. Overriding is an associative operation. It has the empty function as an identity element. If fx, w and gx, w are pointwise equal, for example, the domains of f and g are disjoint, then the union of f and g is defined and is equal to their overriding union. This definition agrees with the definition of union for binary relations.
Inverse function.
An inverse function for f, denoted by f(1), is a function in the opposite direction, from y to x, satisfying. That is, the two possible compositions of f and f(1) need to be the respective identity maps of x and y. As a simple example, if f converts a temperature in degrees Celsius C to degrees Fahrenheit f, the function converting degrees Fahrenheit to degrees Celsius would be a suitable f(1). Such an inverse function exists if and only if f is bijective. In this case, f is called invertible. The notation, or, in some texts, just, and f(1) are akin to multiplication and reciprocal notation. With this analogy, identity functions are like the multiplicative identity, 1, and inverse functions are like reciprocals, hence the notation.
Types of functions. Real-valued functions.
A real-valued function f is one whose codomain is the set of real numbers or a subset thereof. If, in addition, the domain is also a subset of the reals, f is a real-valued function of a real variable. The study of such functions is called real analysis. Real-valued functions enjoy so-called pointwise operations. That is, given two functions where y is a subset of the reals, and x is an arbitrary set, there, pointwise, sum f plus g in product f. G are functions with the same domain and codomain. They are defined by the formulas. In a similar vein, complex analysis studies functions whose domain and codomain are both the set of complex numbers. In most situations, the domain and codomain are understood from context, and only the relationship between the input and outputs is given, but if, then in real variables the domain is limited to non-negative numbers. The following table contains a few particularly important types of real-valued functions.
Further types of functions.
There are many other special classes of functions that are important to particular branches of mathematics, or particular applications. Here is a partial list. Differentiable, integrable, polynomial, rational, algebraic, transcendental, odd or even, convex, monotonic, holomorphic, meromorphic, entire, vector-valued, computable.
Function spaces.
The set of all functions from a set x to a set y is denoted by x, y, by, or by yx. The latter notation is motivated by the fact that, when x and y are finite and of size x and y, then the number of functions x, y is yx equals yx. This is an example of the convention from enumerative combinatorics that provides notations for sets based on their cardinalities. If x is infinite and there is more than one element in y, then there are uncountably many functions from x to y, though only countably many of them can be expressed with a formula or algorithm.
Currying.
An alternative approach to handling functions with multiple arguments is to transform them into a chain of functions that each takes a single argument. For instance, one can interpret add 3, 5, to mean first produce a function that adds 3 to its argument, and then apply the add 3 feet function to 5. This transformation is called currying. Add 3 is curry, add, applied to 3. There is a bijection between the function spaces Caxby and CB, A. When working with curried functions, it is customary to use prefix notation with function application considered left associative, since juxtaposition of multiple arguments, as in fxy, naturally maps to evaluation of a curried function. Conversely, the and symbols are considered to be right associative, so that curried functions may be defined by a notation such as f, z, z, z equals x, y, xy.
Variants and generalizations. Alternative definition of a function.
The above definition of a function from x to y is generally agreed on, however there are two different ways a function is normally defined where the domain x and codomain y are not explicitly or implicitly specified. Usually this is not a problem as the domain and codomain normally will be known. With one definition saying the function defined by f, x, equals x2 on the rails does not completely specify a function as the codomain is not specified, and in the other it is a valid definition. In the other definition, a function is defined as a set of ordered pairs where each first element only occurs once. The domain is the set of all the first elements of a pair and there is no explicit codomain separate from the image. Concepts like surjective have to be refined for such functions, more specifically by saying that a given function is surjective on a given set if its image equals that set. For example, we might say a function f is surjective on the set of real numbers. If a function is defined as a set of ordered pairs with no specific codomain, then f, x, y indicates that f is a function whose domain is x and whose image is a subset of y. This is the case in the ISO standard. Y may be referred to as the codomain, but then any set including the image of f is a valid codomain of f. This is also referred to by saying that f maps x into y. In some usages x and y may subset the ordered pairs, for example a function f on the real numbers such that y equals x2 when used as in f, means the function defined only on the interval. With the definition of a function as an ordered triple, this would always be considered a partial function. An alternative definition of the composite function g, f, x defines it for the set of all x in the domain of f such that f, x, is in the domain of g. Thus the real square root of x2 is a function only defined at 0 where it has the value 0. Functions are commonly defined as a type of relation. A relation from x to y is a set of ordered pairs, x, y, with and. A function from x to y can be described as a relation from x to y that is left total and right unique. However, when x and y are not specified, there is a disagreement about the definition of a relation that parallels that for functions. Normally a relation is just defined as a set of ordered pairs and a correspondence is defined as a triple, x, y, f. However, the distinction between the two is often blurred or a relation is never referred to without specifying the two sets. The definition of a function as a triple defines a function as a type of correspondence, whereas the definition of a function as a set of ordered pairs defines a function as a type of relation. Many operations in set theory, such as the power set, have the class of all sets as their domain, and therefore, although they are informally described as functions, they do not fit the set theoretical definition outlined above, because a class is not necessarily a set. However, some definitions of relations and functions define them as classes of pairs rather than sets of pairs and therefore do include the power set as a function.
Partial and multi-valued functions.
In some parts of mathematics, including recursion theory and functional analysis, it is convenient to study partial functions in which some values of the domain have no association in the graph. That is, single-valued relations. For example, the function f such that f, x, equals 1/x does not define a value for x equals 0, since division by 0 is not defined. Hence f is only a partial function from the real line to the real line. The term total function can be used to stress the fact that every element of the domain does appear as the first element of an ordered pair in the graph. In other parts of mathematics, non-single-valued relations are similarly conflated with functions. These are called multi-valued functions, with the corresponding term single-valued function for ordinary functions.
functions with multiple inputs and outputs.
The concept of function can be extended to an object that takes a combination of two, or more, argument values to a single result. This intuitive concept is formalized by a function whose domain is the Cartesian product of two or more sets. For example, consider the function that associates two integers to their product, f, x, y, equals xy. This function can be defined formally as having domain zxz, the set of all integer pairs. Codomain z. And, for graph, the set of all pairs x, y, xy. Note that the first component of any such pair is itself a pair of integers, while the second component is a single integer. The function value of the pair, x, y, is fx, y. However, it is customary to drop one set of parentheses and consider f, x, y, a function of two variables, x and y. Functions of two variables may be plotted on the three-dimensional Cartesian as ordered triples of the form, x, y, f, x, y. The concept can still further be extended by considering a function that also produces output that is expressed as several variables. For example, consider the integer divide function, with domain zxn and codomain zxn. The resultant, quotient, remainder, pair is a single value in the codomain seen as a Cartesian product.
Binary operations.
The familiar binary operations of arithmetic, addition and multiplication, can be viewed as functions from Rx to R. This view is generalized in abstract algebra, where n functions are used to model the operations of arbitrary algebraic structures. For example, an abstract group is defined as a set X and a function f from x to x that satisfies certain properties. Traditionally, addition and multiplication are written in the infix notation, x plus y and x xy instead of plus, x, y, and x, x, y.
Functors.
The idea of structure-preserving functions, or homomorphisms, led to the abstract notion of morphism, the key concept of category theory. In fact, functions f, x, y are the morphisms in the category of sets, including the empty set. If the domain X is the empty set, then the subset of x xy describing the function is necessarily empty too. However, this is still a well-defined function. Such a function is called an empty function. In particular, the identity function of the empty set is defined, a requirement for sets to form a category. The concept of categorification is an attempt to replace set-theoretic notions by category-theoretic ones. In particular, according to this idea, sets are replaced by categories, while functions between sets are replaced by functors.
History.